Okay, so we're talking more about section 4.2, and 4.2 can get it can get conceptual. I mean, well, everything's conceptual in this course, but I'm trying to make it to give you concrete to go over concrete examples so you can help understand the concepts. And in section 4.2, they have a table. It actually comes after example 7, where they contrast the null space and the column space of a matrix A. And, you know, I think it's a nice reference for you to be aware of. And then, of course, this section is so section 4.2 is the title is null spaces, column spaces, and linear transformations. And we haven't talked about the linear transformations yet. You know what they are, but so how many recall this definition for a linear transformation that you learned that earlier? Okay, remember the linear transformations? The definition of a linear transformation? Sure, Olivia remembers it, Benjamin remembers it. Let me see here. So linear transformations, you learned back in section 1.8. And yes, let me just see here, hold on. Nafani, Benjamin, and Olivia remember it, yeah. So now there's a little bit of terminology that's used with linear transformations. And so we have something called the kernel of a transformation. The kernel of a transformation is the set of all vectors U in a vector space such that T of U equals 0. Okay, so it's a null space, but it's a null space of a transformation. Okay, like for instance, T times X equals A times X. All right. If that's your transformation, then the kernel and the range of the transformation are simply the null space and the column space of A, as you saw earlier. Okay, so if your linear transformation is simply defined as the matrix A, an m by n matrix A times a vector X, then the kernel and range of the transformation are the null and column space of A that you learned earlier. Okay, and it's they have a little picture here in the figure, a little picture below that talks about subspaces associated with a linear transformation. So kernel is a subspace, and the mapping of your transformation is actually a range. The range is a subspace. So the kernel is a subspace of space V. The range is a subspace of space W. And what I want to do is I want to do a little example to reinforce this idea of a kernel of a transformation, but I want to do it with a transformation that's somewhat non-standard. Okay, that because I know in the, like for instance the multiple choice exercises, they'll have you know they'll have conceptual problems where they have different kinds of transformations and so forth. I know. So I want to do an example with you here of this transformation. So let me give you a moment to copy it down, and then we'll go over it. Okay, so, all right, in this problem, we have a transformation where the transformation is taking vectors from this P sub 2 space and mapping them into R sub 2 space. So we know R sub 2 space is vectors in the xy plane. What's P sub 2 stand for? What space is that called? Good, Haley, the polynomial space. It's the polynomial space. So we're mapping polynomials to vectors. And what's the degree, by the way, of the polynomials? P sub 2, what's the degree? Second degree. Good, Nafani. So, you know, we're mapping polynomials from second degree polynomial space to vectors in the xy plane. Essentially, that's what this is, this transformation. And the transformation, you know, it's not, you know, you're used to seeing all the time, you know, the transformation equals a times x, but that's not what this transformation is. This transformation takes vectors in the polynomial space and maps them into vectors whose elements are the polynomial at 0, evaluated at 0 for the first component, and the second component is the same, the polynomial evaluated at 0. So what we want to do is we want to find polynomials P1 and P2 in polynomial space P2 that span the kernel of the transformation. So this kind of problem is really designed to reinforce the definitions of a kernel. Okay, and it takes some thinking, right? So let me go to or if we're good here, I'll go to the solution. Let's look at the solution. Are there any questions so far? Okay. So right off the bat, you know, right from the beginning, I like to, you know, describe my polynomial 2 space. It would consist of all polynomials of second degree polynomials. It's the space of second degree polynomials. Okay, so I'm going to let you copy. That'll get you up to here. All right. I want to wait till you get up to right here, and then I'll make a few more comments. Okay, so, all right, now any quadratic polynomial, and that's what these are, quadratic polynomials, they're degree 2. any quadratic polynomial q of t for which q of 0 equals 0, okay, that means you put t equals 0 in and the polynomial gives you 0, that would be in the kernel of the transformation, because the kernel of the transformation is the null space of the transformation. And so, you know, t of q would, by definition of the transformation, that would be equal to the vector. The transformation takes the polynomial q and maps it to the vector whose components are q of 0, q of 0. Okay, but then what is q of 0? Well, it is 0. So you'll get the 0 vector. So any quadratic polynomial for which q of 0 equals 0 would have to be in the kernel of the transformation. So what would these polynomials look like? Well, the polynomials, the q of t polynomials, would have to be of the form a times t plus b times t squared. Because if you put in t equals 0 into this class of polynomials, q of 0 is equal to a times 0 plus b times 0 squared, and that equals 0. Okay, so that's how you, that's like, those are the polynomials. These polynomials, these q of t polynomials, which equal at plus b times t squared, form the kernel of your transformation. It forms the kernel of your transformation. And so the polynomials then that span the kernel of t would have to be p1 of t equals t and p2 of t equals t squared. I mean, any linear combination of those two second degree polynomials, p of 1 equals t, is a second degree polynomial, because you could write that as t plus 0 times t squared. So any linear combination of these second degree polynomials, p1 and p2, would then give you a vector, that q of t, which comprises those polynomials q of t comprise the kernel of the transformation. And another way to look at it is the kernel, the vectors q of t that comprise the kernel of the transformation are simply linear combinations of p1 of t and p2 of t. And so the vectors p1 of t and p2 of t, which in this case the vectors are polynomials in the second degree polynomial space, the p1 and p2 vectors, those p1 and p2 vectors span the kernel of t. All right, and I know that you have a problem like this in your section 4.2 homework. I think it's in the multiple choice, and I'm sort of assuming nobody got to that yet. So I'm sorry if you maybe accidentally missed it. I hope you didn't when you were working on the classwork. I assume, from what I can see, it looks like you were, you were focused on the three responses, right? So, but how many think this is kind of an interesting example? Okay, Benjamin likes it. Ariana, Olivia, yeah, and you know, it's theoretical, but if we think in our minds about like concrete examples, it helps us. Are there any questions on that? Are there any questions on that? All right, let me stop the recording.